today we are going to do section 5.4 on page 161. This page was already scanned earlier, so I will just focus mostly on this part, and that should be good. Next, 162 and 163. All right, that is this. Let's see, let me keep it somewhat parallel here. That's the whole page. Okay, and then a bit closer on top. And then a bit closer on the bottom. Okay, so that should do it. And finally, 164 and 165. So here are the pages. Let's see. Okay, and then hold it a little closer on top. And a little bit closer on the bottom. Okay, so that should do it. So today we're going to start at section 5.4. The first thing I want to show you, actually I forgot to grab it. I want to show you the Cauchy's, what is this called? The Cauchy's convergence criterion, which says if you have a sequence, right, and the sequence will be convergent if the tail end gets close to each other. That is, if it converges for every epsilon, there exists some big number n such that for all n and m that are big enough, that are bigger than n, every single n and m are going to be right next to each other. Okay, then that will mean the series converges. If you think about that, the thing is converging, then they're all coming to the same point, so obviously they're going to be close to each other. And so, however, I wasn't able to find this in Calculus 2 or 3, so and then the internet says that this isn't even taught in beginning calculus. Yeah, and I thought it used to be taught, maybe. So they just don't teach it anymore. Either way, the point is, we're gonna need this thing at in this section. So that's why I want to mention it. That just remember that to prove a sequence is gonna converge to a point, right? That you can simply prove that all the members in the tail end of the sequence will be close to each other, okay, within an epsilon distance, as long as for every single thing on the tail end, okay, as long as you go out far enough in the tail, then everything is within however small a neighborhood you want to choose, an epsilon neighborhood. So that is called the Cauchy convergence criterion. It doesn't really matter what it's called. What matters is that you realize why that would be true. But we will prove this thing officially in the next section or two. But the book wants to use it now, so I want to tell you about this. So having said that, let's look at page 101. So in this section, we're going to do the law of the mean. Okay, now first there is a quick introduction paragraph, which I will ask you to read this paragraph yourself. Okay, and then we will turn to the next page where we'll consider theorem 3. Now let's look at the first the mean value theorem. Theorem 3 states that let's say f is continuous and alpha is going up, okay, that is non-decreasing. And this also works for going down, by the way, but we'll think about that later. Right now, we'll focus on the case where it would go up. Now then, that means that the integral of f is got d alpha. You can yank f out of there, okay, with some value between a and b, and just left with the integral. Now we already had this thing. This is called the mean value theorem for integrals, but we'll talk about that a little later. So, but this time, of course, we're doing the Stieltjes integral. However, the proof is basically the same too. So to look at the proof, and we will set f being continuous, we're able to find its maximum and minimum on the interval. And then by property, we'll look at property 7, and on page 155, we'll look at property 7 and 1. Okay, so let's look at property 7, which states something about inequalities. Yep, I knew it. See, if f1 is less than f2, that means the integrals are less also, of course. And then property 1 says if their f is equal to 1, then the integral is just the endpoint subtracting. So bearing in mind those two properties, we come back to our page of 162. Then we can slap this thing, slap the integral in there, okay? Being that f is between those two things, when we slap the integral on, then by property 7, it is n1, okay? So that's the integral, and then we can claim that the integral is equal to m times and the value, well, m times the limits, okay, of a small m and a big M. I should probably mention that we're also using condition 3, right? Because you can then pull the constant out. Basically, we're integrating the constant by pulling it out. So we're using condition, what is that called? Property 1, 3, and 7 to do this. Now, so if you look at this for a few moments, then you realize it. And so, well, there are two possibilities. Either alpha b equal to alpha a, in which case this inequality will become equality. Doesn't matter what you pick for psi. So that'll work. Now, now next consideration is what if alpha b doesn't equal to alpha a? Then we can then set psi equal to f of psi equal to the division. That is, we'll divide everything by psi b minus psi a in this inequality. Okay, put this thing in the denominator across the board. That will reduce the equation into where is it? That will reduce the equation into well, actually the book didn't write it down, but that will establish that the function f is going to be between the small m and the big M once you have done the division. The thing is, at this point we need to quote the intermediate value theorem, okay, which we have not officially introduced, but we'll be doing that at some point. Let's see, yeah. But for now, we'll just quote the intermediate value theorem. So as something we already know. Since the continuous function f of x takes on every value between m and m, small m and big M, in the interval a and b, so that's the intermediate value theorem, then we can find a psi. So this is to be able to nail it, right? Like, does this thing even exist? So we can find f of psi, and that will be this exact value right here, being that this value is between small m and big M. So once we find this value, then plug f of so once we define f of psi as this thing, right? Then we have a set. Then f of psi as defined will satisfy what we are trying to prove. That is that this particular equation, okay, is exactly equals to that this f of psi will be satisfying that condition. Being that psi b minus psi a to the power minus 1 is exactly this integral right here, integral of a to b of d alpha x, and that's by property 1. So that should be the proof of theorem 3, and as you can see, it's quite similar to something that we've done already. And we will actually specify that fact in the corollary 3. The corollary 3 has already been proven on page 44 of the book, but we'll do it again. Okay. So let's say f and g are continuous, and g has to be bigger than 0. Now that is quite a strong demanding requirement, that g has to be bigger than 0. But anyway, g has to be bigger than 0. Fine. So if that is true, then you can yank the f out of there with some kind of psi, as it shows here. Now to prove that, then the first thing we do is define alpha of x as we're going to use theorem 3, right? So we're going to define some kind of alpha x, and we're going to define alpha x equal to the integral of a to x of g of t dt. Now, at that, so in other words, when you see any integral looking like that, you know you're going to be doing the fundamental theorem of calculus. So we are going to, once we have defined alpha, which I've written over here, okay, alpha x is a to the x gt dt, then being that g is bigger than 0, alpha x must be increasing, right? And then alpha prime is equal to g by the fundamental theorem. And then with that, then let's consider theorem 2 on page, it's not even theorem 2, it's just equation 2 on page 156. Let's go back and look at that thing that we've seen several times already. But let's look at it again, okay? Now we have this condition that if f is c and alpha is c1, okay, very strict conditions, then f d alpha is the same as f alpha prime dx. That is, alpha d alpha turns into alpha prime dx. Okay, yeah, kind of like the chain rule, so to speak. So then following that rule, we can let's see, I have written here. We have following. Then this thing equals to alpha prime, and alpha prime is, of course, gx dx. And which means that if that is the case, and g satisfies our conditions of theorem 3, then we can yank f psi out of there. So that, I think that is the end of, is that what we're trying to look for? I think so. Okay, but first I need to get to the right page. Okay, so then this is alpha, as defined by equation 4, is non-decreasing. Okay, and then that's the end of our proof. Now, psi may always be chosen different from a and b. That is something we'll prove later. Okay, that is a matter of well, continuous functions and stuff. So we'll just ignore that for now. So psi can be different from a and b, but however, in equation 1, you can, that is in theorem 3, the mean value theorem, there's no guarantee that you can always find psi that's not the endpoint. That psi might be endpoint. And in fact, to consider an example of psi being an endpoint, you just pick alpha as a step function, like all the step functions we've been doing, and choose f of x equal to x. And if you do that, then you realize, and certain other conditions, that you quickly realize that your psi you might be forced to pick psi as one of the endpoints because no other point is good enough. And like I have an example written here, like if you let f of x equal to x and alpha x equal to this step function, and you see always those step functions that will cause you a headache. Okay, so then among other things, this thing is you're forcing it to, if you have to yank f out, then it has to be f of 0 times this other stuff. Okay, so that is that. I will finish this section in the next video. Yeah, I only had 2 hours of sleep last night, so I'm going to go take a nap now.